This problem concerns approximating a binomial random variable with a normal random variable. So here's the setup. A city has 74,806 registered vehicles. Vehicle owners pay a $50 wheel tax in the month of their birthday. The budget assumes that at least $306,000 in wheel taxes will be collected in November. What's the probability of a budget shortfall in the month of November? So let's let X be the number of vehicles whose wheel tax is paid in November. Now, there are 74,806 possible vehicles. We can think of this as a binomial random variable where there are 74,806 trials, independent, okay, so 74,806 independent trials. And let's assume, it's reasonable to assume, that the probability of a vehicle having its wheel tax paid in the month of November is 1/12. What we're doing there is we're assuming that roughly 1/12 of all birthdays come in November. So the probability of success being the wheel tax is paid in November, is 1/12. Okay, so then the probability distribution for X would just be a binomial one. So we'd have 74,806 choose X, 1/12 to the power of X, and then 11/12, 1 minus 1/12 to the power of 74,806 minus X. So this is the probability that the number of vehicles whose wheel tax is paid in November is equal to the specific value, X. Okay, so the probability of a budget shortfall then is the probability. So what's the revenue collected in taxes? Well, it's the number of vehicles whose tax is paid in November, that's X, times 50. Each vehicle pays $50. So this is the probability that revenue is strictly less than $306,000. Okay. Now we can rearrange this to be simply the probability, just divide both sides of that inequality by 50. This is the probability that X is less than 6120. Come over here. This is the probability that X is less than or equal to 6119. And so since X is a binomial random variable, this would be this monster of a summation. So from X equals 0 up to 6119, 74,806, choose X, times 1/12 to the power of X, times 11/12 to the power of 74,806 minus X. But evidently this is unwieldy at best and a nightmare at worst. So we don't want to compute this. Instead, let's approximate X by a normal distribution. So let's work out, so we know that we can do this under certain conditions. So let's work out n times p, and this is what we're going to take as our expected value, as our mean. So n times p is 74,806 times 1/12, and that works out to 6,233.8. And then what about the variance? This we compute as np times 1 minus p, so this is 74,806 times 1/12 times 11/12, and this works out to 5714.3. Okay, So we're going to say x is approximated by the normal distribution with mean 6233.8 and variance 5714.3. Now, here's where we need to be a little bit careful. We are going to standardize x and look up a value in a table for the standard normal distribution. But before we do so, we need to remember x is strictly speaking, it's a binomial random variable, and it takes on integer values. So over here, actually let me adjust this just a little bit. Over here, if we were to imagine the probability distribution for x, we could do a histogram, and we'd be looking at something maybe like this. Okay, and the mean here would be roughly around 6233.8. But this is what we're going to approximate with a normal distribution. But we need to remember, oh, that's kind of a poor curve. Let me try that again. Since we're going to look up the probability that x is less than or equal to, what did we have? 6,119. So say that's sitting here, 6119. Well, in the binomial probability histogram, this 6119 would be centered in that rectangle. So in order to approximate the area under these bars, okay, so the area under these bars is what would be this here. I'll circle that expression in green. That's the probability that x is less than or equal to 6,119. If we're going to approximate x with a normal distribution, we then actually need to look at the upper side of this rectangle. So I'll squeeze this in here. We need to look at the right-hand side of that rectangle, which is 6,119.5. So that will, because then when we use our table for the normal distribution, that will give us the area under this curve, which is approximately equal to the area under those green rectangles. Okay, so then we're going to have the probability of a budget shortfall is going to be the probability that x is less than or equal to 6,119.5. Here we are using what's called the continuity correction, okay? And now we're going to standardize this. So this we're going to subtract mu and divide by sigma. Where mu and sigma are as above. Maybe I'll circle them here in purple. Okay, so this is the probability that x minus 6233.8 over, so it's the variance that's 5714.3, so we need the square root of that. Square root of 5714.3 is less than or equal to, okay, well, so rather than, I could write in 6233.8 there, but let's just work it out. After you work that out, you're going to get a value of minus 1.51. Okay, but this is what we call z. So z is x minus mu over sigma. So we're looking at the probability that z is less than or equal to minus 1.51, and this now is what we can look up in a table for the standard normal distribution, and we find that this is approximately 0.0655. So there's about a 6.5% chance of a budget shortfall.